Hello everyone. No. Okay, let's try this. Okay, it's hard. Maximum spending after buying items. Okay, so let's try this out. Okay, I see we have an MON matrix. Okay. So, beam, bam. Alright, so you're given 0 indexes to be on an index set matrix values. Pick on any shop. Right, so we have an M on n matrix value, so where each row is sorted is in non-increasing order. So it means values I and j bigger or equal values I and j plus 1. So each day d from 1 to MON we buy exactly one item. So it means let's try this out. Test this on the first 10 8 6 4 2 9 7 5 3 2. Right, so choosing a shop I and buy its current right mouse and bottom G, and we pay values I and the G on D, so we must buy all items and maximize total spending. Right, so let's multi-set of all item values by be like this. Boo, boo, boo. So G equals 0, minus n minus 2 1. Okay, let n equal m on n. So we're assigning each about item to a unique day. It's d 1 and n. So if an item which base value x is bought on day, its contribution is p x d equal x on d. So we seek a feasible permutation of all items maximizing. So it's f e. Alright, f k equal 1 1 n x k on d k. Alright, so but the feasibility is constrained by row order. Alright, so for every fixed shop I, if J1 is lower than J2, then item I J2 must be bought earlier than I J1. So because we're always removed from the right. So in each row, purchase order is forced to be I n minus 1 and some values in values I n minus 2. So and and then we got a values I0. So let's define our versatile sequence. RI T values I n minus 1 minus t. So then t e o n minus 1. Right, so at any moment we may choose as the first not yet used element from one of these m sequences. So thus the problem is merge m non-decreasing sequences so into one global sequence maximizing. So it's if e k equal 1, and then n a k on k. So it's a sense coefficient satisfy. It's 1 lower than 2 and lower than and lower than n. So it's a rearrangement principle. The optimal global sequence is non-decreasing. So the smaller values should get smaller multipliers. Larger values should get larger multipliers. So we need the lexicographic value wise small is feasible in the item at each step. So we always pick the current available minimum and grow tails. So what I need to do? So I think I can use a priority creator. It's with greater. It's a min heap, and I mean each heap node stores a current value, row index, and column index. So for each row I insert as a Bible the item is the rightmost one column min and minus one. So with the push values I now I minus one and I and the n minus one. Alright, so then for the d equal 1 mon, so we extract minimum available value xig and we add x on d to answer. So if row I still has left neighbor, it's j minus 1 bigger or equal 0. We push these values I j minus 1 I j minus 1 and so we complete the task. Alright, so this is let's turn to the mathematical formulation. So we need to use a single row is in A3 array int 3. Alright, so good. Now priority A3 vector and A3. Alright, so good. Greater A3 Q. Okay, and M. So the single column equal values and the larger answer. Let's say we use long. I think we can. Yeah, we can use the long. Okay. Value size and equal values 0 dot size. So for int I0 I is lower than m I plus plus keep push values I n minus 1 I n minus 1. Alright, good. So now long 0 d 1. Now we use q empty, and then after vig we need to use it to top and q pop. So r I1 hello 1 and the d plus plus. Good. Q push values I g minus 1 and then I g minus 1. Alright, good. Now we return R. Let's test this out. I'm sorry. Oh. G u push values I j minus 1 I j the void J I G minus 1 I G minus 1. Wait a minute. What? Uh. Mhm. Char error value. Oh, value type is not contextually convertible to bool. G to the to. Alright. So let me think. We use periodic array. It heap non-stars value local. So one state is values ig. Uh, hmm. Okay, maybe we can use if g if g just got the compile error. Alright, good. Oh, it's perfect. Alright, so what we can do? um, let's submit it. Alright, 71 ms bits, 29%. So okay, let me explain you. Um, you need to imagine there are several boxes of candies. So I mean, um, in each box you can only take the candy from the far right. It's mean each next day uh, multiply the candy price by a bigger number. So I mean day one it's on 1. So day 2 it's on 2. Day 3 it's on 3. So if you want to spend the most, you should take small candies early and save big candies for later. So why? Because the guy giving a big multiplier to a big number makes more money, right? Right. So every day we ask this. No, we ask yourself among all candies I'm allowed to take right now which one is the smallest. So take that one now, save the expensive ones for later. The heap is just like a basket, and that always tells us the smallest available candy quickly. So yeah, it's correctly correct. Goodbye.